Welcome to Beginner's Night on Reverse Engineering. So who am I? I'm Nic Losby. I also go by Blurb Dust online. If you know me, I'm probably your TA, and I'm also just a random person that likes breaking things. So what is reverse engineering? Definition by Wikipedia is it's the process by which a man-made object is deconstructed to reveal its design, architecture, or to extract knowledge from the object, similar to scientific research. And so reworded, it's basically just trying to figure out how someone made something to either reproduce it, break it, or to understand it. So why reverse engineer something? Maybe you lost the source code of a program, Microsoft. Or maybe you want to try to understand what the program is doing, so you can either A, copy it, or B, exploit it. So you're going to need a lot of tools for this. So there's some very large dollar number for IDA Pro. It is around $15,000 or so for everything. There is an IDA free version, and it is pretty good still. You don't get the decompilation part, and I'll show you that later. But IDA free is still really good. Then there's Binary Ninja, which is my go-to for now. But it's $150, and this is student price. Hopper v4 is $100. Radare 2 with a Cutter GUI is free. And as of today, G-Hydra, which is also free. And I'll try to get it to run later, but we'll see. It literally came out an hour ago. You'll also need a debugger, preferably GDB if you are on Linux or Unix systems, and then with an extension of either pwndebug, PETA, or FG's GDB in it. You'll see pwndebug in action later, and you can see that it's much better than just stock GDB if you're exploiting things, or for debugging things as well. If you're on Windows, Immunity Debugger is really good, so is Ollie Debug, and also x86 debug and WinDebug. There's a lot more stuff for Windows. So really quick, where can I find more information after this talk? This should actually go at the end, but I forgot to move it. Live Overflow, you'll hear me say his name over and over and over. It's because it's a really good resource and he's awesome. Gynovale on his English channel has a lot of good stuff. And a new one that I found, MurmaCTF, is pretty good too. He does a lot more streaming, so it's more like 2 to 4 hour long videos. But if you just put it on in the background, you'll pick up stuff in the background. So quick overview of what we're going to talk about. So someone hands you a file. They tell you it's an executable file meant for Linux. So what are you going to do? You're going to run file on this file. That'll tell you what kind of file it is. How does it know what kind of file it is? Well, because of the magic number. It's in the very first up to 8 bytes of the actual file itself. So how can you see that? If you're on XXD, which is a hex dump program, you run it on that file, check out the first 20 lines, you'll see it right there. I'll show you examples in a little bit. And then hopefully you can run the binary with valid input. You should always assume it's malicious and run it in a VM. And then your next step after this is to figure out what the binary should do. Like, should it connect to the internet? Should it just be a calculator? Is it a license program that you need to find a valid key for? So I always look at binaries through different lenses. So if I'm just trying to understand it, like if I'm debugging my own broken code, then I go through the understanding lens. So I check everything. I check all of the code paths. I try to see what function does what, if that function should be doing that thing. And then if it's loading files, I try to find out how things are being loaded. But if I'm looking through an exploitation lens, I check if there's any path where the program gets input from the user. So then I try to follow that path and get to that path. So say it's an email program. You're trying to click the new email button so then you can start typing things, basically like that. And then continuing steps, basically you only go here if you're trying to recreate it, so then you just type up the source as you go, as you understand the program. So quick little detour. It's not actually a detour, it's very relevant. Background info on some files. So ELF is the executable linking format. The magic number that I was talking about earlier for an ELF is 0x7f4546, and that is ELF in hex. So if you run XXD like I showed earlier, you'll actually see the magic number right here. So the file format of an ELF you can find on Wikipedia, but essentially it is you have your ELF header, then your program header table, and then your text section, which is where all of your code is stored as assembly. And then you have your RO data, which is your read-only data. These are your global variables. And then you have your data section, and this is where all of the local variables for each function sit. And then you have your section header, which just tells either GDB or whatever's executing this file more information. Like, hey, if I crashed at address 400, then that's within this function called print flag or something. And then your entry point is always _start. So when I get a file, I run checksec on it. Checksec can tell you about the security of it, and you check the security. So relro, this will come for exploitation on April 6th. It means we can write to the GOT, which is the global offset table. Skip over that for now. I'll reuse this slide later. There's a stat canary, which is very pertinent for exploitation. And then NX means there's a not executable stack. And then PIE, or position independent execution, also known as position independent code, means that the virtual address that the code is being run at doesn't change ever. So with modern exploit mitigation techniques such as ASLR, address space layout randomization, I talked about this during my kernel exploitation talk, it'll actually change where in memory it is every single time. In this case, this binary does not do that, so we don't have to worry about that. If you are decompiling something locally, just know that if you're trying to exploit it, the address will change when you're actually running it somewhere else, if PIE is enabled. So with a ELF parser, such as Binary Ninja or read ELF, this is just what the ELF header looks like. One fun thing to do is to write your own, and I have done that. That is not shown because it kind of sucks, but I did do it for the Play 9 stuff, and that it actually works very well. But yeah, so this is what the header looks like, and it tells you a bunch of information about the actual file format itself. If you want to figure out what's going on with ELFs and what actually gets loaded into memory when you run it, this is a really good exercise to do. So quick little overview about registers. So your EAX through EDX are just your general purpose registers. Registers are just hardware that stores temporary values for your program to execute. That stores temporary values that get written to by the program that is executing. ESP is the stack pointer. EBP is a stack base pointer, so it just tells you where the stack is, and then the ESP can move from that. So each function that you execute has its own stack, and ESP changes for each of that. Your segment registers, we can skip over that. It's not necessary at this point. It will come in handy on April 6th. And then miscellaneous registers such as EIP, that is the instruction pointer register, and that tells you where you are currently, like what instruction is currently being executed. And then you have E-flags, which if you run any compares or jumps, then it will show you okay, so if you're running compare on, say, EAX and EAX, and if they are not equal, then it will set the 0 flag. So, and that is within the E flags. That'll show up later. And then you have your status flags, which are included inside the E flags. And then in older hardware, your EAX is actually just AX. And that's in 16-bit. In 64-bit, you have the RAX. So if you replace E's with R's, if you're in 64-bit, then you'll have RAX, RCX, RBX, RDX, and RIP. Okay. Ton of info. Anyone lost? Remember, this is beginner's night. You can shout things out, ask questions. All good? I'm gonna grab some water.
Can you explain the ELF header, like go back over
Yeah.
a little bit?
So when you're executing the file, the kernel needs to know what to load where. Like, Where am I going to map variables to? Where am I going to map this actual executable part to? And so you run through and you have to tell the kernel what architecture it's targeting. So if you're on a 64-bit machine and it comes across a 32-bit executable and you don't have multi-libs installed, it's going to be like, I don't know what this is. I can't help you. And then you'd be like, the file's right there. What do you mean no such file? That's the error that'll come up. So this is telling the kernel right here, hey, this is 32-bit. So if the kernel doesn't know what's going on, then it'll be like, yeah, there's nothing here. I don't know what you're talking about. This is where certain offsets, so it's loading parts of the ELF into certain parts of RAM, basically. And this is telling it where to load it to. Any initialization flags, and the size of this header itself. And then how many strings are included in it, how many hard-coded English words, basically. Yeah, and it just keeps going on and on. Does that answer it for the most part? All right, cool. Okay, so how I reverse engineer binaries. First, I run file on it. Tells me if it's 32-bit, 64-bit, if it's an ELF executable, if it's a PE, which is a portable executable meant for Windows. It tells you a whole bunch of information. Documents to reverse. So we will actually be playing with one given to us by Jake Drehos at SecDSM. So if I run file on it, it tells me it's an ELF, it's 32-bit, it is least significant bit, so that is the endianness of it, and it's targeted to the Intel 8386 architecture, so 32-bit, x86. And it's version 1 of the ELF, and there's only one version, so it's kind of moot. It's statically linked, which means it includes all of the required libraries for the program to execute. So if we check out the size, you can see it is 4 megabytes. And that is pretty large for how small this program actually is.
So statically linked meant that all the libraries are included in
Correct.
Okay.
Yes. Yeah. And then we can run checksec against it. So that'll show us if there's any security set for this. You actually already saw the screenshot earlier. It's partial rel-row, non-executable stack, no pi, and there is a stack canary, which if you exploit this, and we'll show you how on April 6th, there's a neat little trick. Since it is only partial rel-row, when you smash the stack, it'll say, there will be a function called check stack guard, and you can just overwrite past that. So it doesn't matter. It's really funny. And then there's strings, and that tells you any ASCII strings within it. So if there's any debug output saying like, this value should never be null, you can try to find that in memory, and it'll strings, and it'll show you that. So there's a bunch of debug info included since it's statically linked, so it's pretty noisy. But I know if you look for hello, it's included in there. So there somewhere within this binary is the string hello. And if I just scrolled through the whole thing and not be impatient, then we would have noticed that. So then I open the file in a disassembler, and I'll show you a bunch of disassemblers in a second. And then I start at the start, and then I go to main, and I just do breadth first search. So I go to every single function that's called within main, and then every single function that's called from those functions that are called within main. Usually by then you're through the whole binary, unless it's huge. I tried reverse engineering CSGO for a bit, and it was so bad because it was so big. It is 6 gigabytes of executable stuffs, and I gave up. That wasn't fun. So when I reverse engineer things, it's usually with an exploitation lens. So as soon as I find the first bug, that's it. I'm done. I'm gonna try to exploit that. So Detour, which is a comparison of all the tools. So this is Binary Ninja. This is the graph view. I'll get to exactly what each of these things mean in a second, but visually it shows you there's a nice little loop. And if you have a variable, we'll call it variable 14, and we compare it against a different variable, And then at the very end, we increment that variable by 1. What's that sound like? Sounds like a little for loop going on. If I is less than 18, keep going. And until I is greater than 18, so jump if less than. So if that becomes false in red, then we move on. So that for loop is done. It doesn't really matter what's in between here. We just can see there's a for loop. This is the same thing in Verdare. This is one of the free ones that I was talking about earlier. Kind of looks a little less good. You can still visually see this loop, and it still tells you there's a local check, and it increments by 1 every single time. And then this is Hopper. This is the $100 software. And it does the same thing, but it kind of looks a little weird. The graph could be better, in my opinion. And blue means loop in here as well. And then this is IDA Pro. This is the quintessential like $15,000 industry standard. To me, it looks really nice and pretty. And it actually, since there's so much debugging output included in it, it'll tell you the name of the variable that you're using. It'll tell you the name of the function that it's going to call. So I find that really cool. But one special thing about IDA Pro and why it costs so much money is it can give you back pseudo-C. So it gives you basically the same, depending on if there's any obfuscation, but basically the same source that went into it. And it's doing this from guesses. It's not, the source code isn't included within the file itself. It's just seeing all of these behaviors, and it's like, this kind of looks like this C function, so I'm gonna put that there. So actually, on the left is the given source that Drehos wrote. On the right is what IDA Pro came up with. And you can see it's pretty much one for one. Set buff, make keep executable. And we even have a for loop here. So for I equals 0, less than length, I++. This change right here is due to compiler optimizations. So the compiler was like, I can make this better. So that's why it's different just a little bit. But it's pretty much the same thing. And you can see it handles this part really, really well, line 10. It's exactly that. I didn't edit this whatsoever.
How well does this work for non-C code?
For Go, it sucks. Those are the only ones you'll be really reverse engineering with IDA. If it's Java, you can decompile it a lot better. There's tools that will destroy IDA in that part. But IDA is really meant for C, C++, and kinda Go, because they're all compiled binaries. So how does the $15,000 software compare to others? Well, here's Binary Ninja. It doesn't even have decompilation features. This is the closest you can get with it. It's called the Medium IIL, Medium Instruction Link Layer something. And you can see, it does see, there's a for loop here. So if it's less than 18, then go here, otherwise go here. But other than that, it just kind of looks bad. You don't get anything really useful out of it. Definitely not what you get out of IDA. Hopper is the other one that has pseudocode, but it's really not readable. If you do copy this out and try to edit it a little bit, and you make the guess of EBP minus 0xC is probably I, because you do I equals 0, I is less than other variable. You can edit it, make it look a little bit better, but out of the box, it's nowhere near IDA. And then here's Verdare, and it's like, hey, that's a while loop, right? And Verdare is the free one. You actually have two different decompilers with Verdare. It kind of sucks, and it doesn't look good at all. So that's why you buy the $15,000 software, because if you want to be lazy and you don't want to have to read assembly all day, you can just read almost C, and it's almost C. Here's the other one, it looks worse. So just don't decompile with Verdare. If you really need to decompile things, Hopper, if you put some time into it, it'll still be faster than reading the assembly itself. Yeah, so reading the assembly. This is the start function of the same binary. So you see it XORs EBP with EBP, just clearing it out, and then it does a whole bunch of other things. So pop and push are functions to and from the stack. So pop pulls things from the stack to a register, and push puts that register content onto the stack. Function calls can have many, many arguments, and if you only have, say, 8 general purpose registers, EAX through EDX plus a few others, how can you have more than 8 arguments to a function? Well, you got to put everything on the stack then. So you can see we're setting up a function call right here. So we push the register value, push the register value, push a third argument, and then we call this new function. Functions will always be described as sub and then their memory address, unless it's IDA who can resolve that, but basically no one else can do that. GHydra is supposed to be able to, so that's why I want to look at it. Yeah. So one of the things that I always mess up is move is from destination to source. So here, you're moving main into EAX. You're not moving EAX to main. You're moving main to EAX. And normally that should be a hex number, but Binary Ninja was able to resolve this function call, but it wasn't able to resolve the other one. Like I said, they're still working on that part of it. The quintessential source for all things assembly is the Intel Assembler Programming Handbook, and there's 8 volumes, each with A and Bs, and it's just a lot of stuff, and I've only ever opened it twice. But from the 2 times that I've opened it, it's very good. It will teach you a lot. There's a class here that is supposed to teach you assembly, Computer E381. I use supposed to for a reason. Yeah. So let's actually try to figure out what some of those instructions are, because I'm sure we're a little bit lost, and that is okay, because I was too when I first did this. So we have this open in GDB with the pwn_debug extension. So we can see up here, we have our memory map, all of our registers. We can see our current executing instruction, and then we can see our stack right here. So if I back this up, you can see the very first thing that we're going to execute is XOR EBP EBP, and that is highlighted right here. It's just a little bit brighter than the others. So XORing EBP by EBP is going to XOR itself with itself, so it's going to clear it to 0. Well, it's already 0, but you can see EBP up here. And so after this function call, or after this instruction executes, it's going to be 0. It's still 0. Woo. And then we're going to pop ESI. So remember, we're taking from the stack and putting it into ESI. So you can see down here, the thing that's at the top of the stack is 0x1. So we're going to single step in this instruction, and you see ESI here. So as soon as it executes, now you have 0x1 there, and now it's off of the stack because you popped it. So we're going to move from ESP to ECX. So ESP currently is what's pointing to my home directory. So we're going to go ahead and move it whenever I decide to do it in the video. There it goes. And so now you can see ESP and ECX have the same thing. So it's just copying it from here to there. And then we will AND ESP with basically -1. We're just trying to find the last bit, and that's why you AND by a large number. So it'll clear out ESP and just leave a 1. And then we will start pushing some arguments to set up this function call of start. So we will do push EAX, and remember it takes the register content and puts it onto the stack. So I'll go ahead and back up a little bit. So EAX currently is 0. So we're going to push EAX, and it's still 0 because it already was 0, but now we have a 0 on the stack. And then we're going to push ESP. So push from ESP onto the stack, and now you have the same thing here. And then we're going to push EDX. So we're taking the value in EDX, which is a 0, and we put it onto the stack. So now we have another 0 on top of the stack. So I mentioned each function has its own stack. So when you push things onto the stack, it'll then, once you get into that new function, it'll start up its own stack. So you can keep putting things on top of the stack, but then when that function returns, it'll take off as much as it put on. So the reason we're setting things up on the stack is it gets, not only does it get its arguments from the stack, but it also stores information, such as like the previous return address, which is where we are currently. So if you notice right here, this memory address 80499 dB, if we return from this function call, we'll come back to here because we put that onto the stack, and that happens soon. But I'm just going to step over that because I don't want to decompile this function further. So I'm showing you that you can do many, many things, and you just set things up as you go. And if you're wondering like how reverse engineering actually is, you're wondering if it's magic, no, it's this. It's you read that line by line, and you figure out where things are going in memory. Like, that's it. It's super time consuming. You just keep going. And then you try to figure out exactly what the program is doing. Things like IDA help with that and make it faster, but you can just step through it and you see exactly what it's doing. So if you want to go towards the exploit development side, you can try to find where there's going to be a bug. I should probably skip over this part and come back to it later. But yeah, so we'll go through a little bit more of this. I already talked about the for loop. So you set I, which is variable 14, to 0, and then you jump into the for loop, jump to this memory address. So you're at this memory address now, and you move I to EDX, and then you compare, or EAX, you compare EAX to memory offset from the base pointer. So it's on the stack, and you treat it like it's a pointer, and that's what the brackets mean.
So it's 10 down in the stack or up? Do you count the stack from the top to the bottom or the bottom to the top? Because it's 0 times 10?
Top to the bottom.
Top to the bottom.
It's technically 18.
Okay.
Yeah, technically 18, 0x 10, but 8.
Okay.
Wait, that's 16. You count X numbers from, I don't know why it's 18 then. That's weird, and this is 12, and that's, whatever. And then, so you compare them, and if the 0 flag is set, that means it is less than or equal to, so it'll jump less than, and then it'll do things here. And if you remember from the source code a while back, it just sets static buffer at that offset, and it ends it with the opposite of 0x20. But it's just doing things to it. That's all that matters. Yeah. So in action, if you're given, say, a license key program, this is how they crack Microsoft Word or like Adobe products. They start up the program in a debugger, and then they'll set a breakpoint in main. So it'll skip over all of the function initialization stuff. Like it's telling the kernel like, hey, things are here and here and here. And we can just skip over that. And then I see in here it's calling a function called verify keys. So I'm just going to go ahead and set a breakpoint right there because that's what we really want. So I'll copy it, set a breakpoint by typing break, and then the value I'm about to type I want to treat it like a pointer. So I put a little asterisk, and then I copy and paste the value there. So now there's a breakpoint set. So when we run, and we do that with R, it'll execute as far as it can get to that breakpoint, and then it'll pause execution there. In this case, it calls fgets, so that's input from the user. So this is going to be where it's trying to get the product key. And because I like exploiting things, I just use a whole bunch of A's, because that's what you normally do, because it's really easy to see A in your memory layout right here. So we hit our breakpoint, we're at call verify key, so we're gonna go ahead and step into that function by just typing S, or SI, single instruction. And then this is where it sets up stuff. It creates its new stack, and then now that it has its own stack and we can start writing things to it, it is going to call string length on the input that we gave it. So this license checker is trying to find the length of the input that we gave it. So I'll step over it so we don't disassemble that part, because it would be like hundreds of lines. We can just skip over it. We know what string length does based on the man page. And then it's going to compare the result, which is stored in RAX, that is in the man page of string length, with a hard-coded 0x1c. And that is 28. So we, by chance, typed in 29 characters. And so it is, in fact, greater than or equal to 28. So we passed the first check accidentally. So cool, that's great. So you see it'll automatically tell you where we're going to continue execution to. So I'll just go ahead and, yeah, it's saying, hey, you passed that check, so it gives you a little check mark. Great. So now we are going to take the user input and treat it like a pointer. I'm gonna need chalk for this part, I think. And then it will go ahead and start up check 1. So we passed the first check, and that was just if it's longer than 28. So we know the key is at least 28 bytes long. I won't write that yet. So then it sets up its own function stack, and then it takes the user input and adds 5 to that offset. So remember in C, if you have a buffer, car star buffer, the start of it, so if it's A, B, C, the index is 0. So if you do buff plus 0, we're referencing this A right here. If you do buff plus 5, then it'll be referencing 0, 1, 2, 3, 4, 5. So it'll be referencing this F. So it's taking our input, and then it's loading 5 onto it, and then treating it like a pointer. And then it will compare what it is. I'll just keep going. So you'll notice up here is all of our A's as input. And then it takes the 5th element. So now it's just 1 A, because remember we gave it 29 A's. And then it compares that. AL is the lower 8 bits of RAX. That was in the registered cheat sheet. And it compares it to 0x2D. Well, 0x2D is a hyphen. How do I know that? ASCII table. It'll tell you the decimal and hexadecimal equivalent to each character. So we look it up. 0x25. Oh, that's.
Wasn't it 2D?
2D, yes. You are correct. 0x2D, that's a hyphen. Thank you. I knew I was right on that. So compares it against 2D, which is a hyphen. So it's checking if this 5th character is a hyphen. So we know valid input, this now has to be a hyphen. Okay, cool. And in this case, it sees, hey, that's an A, that's not a hyphen. It's just gonna quit out on us. So I noticed that and I was like, oh man, I messed up the demo. So I just kind of sit there for a little bit, and I'm like, okay, fine. I'll show what happens when you end execution. So I set a breakpoint to come back to that, and then I just restart execution from there. So then I continue through it. So I don't know what input it wants now, but I know there has to be a hyphen there. So I'm just going to give it all hyphens and make sure there's at least 28 of them. So I'll just hold down the hyphen key for a little bit, and then I'll start up, and we hit a previous breakpoint of verify key. So we're going to go back through the same process. We're going to go into verify key, and then we're going to go into check one. And I had messed up something, and my breakpoint wasn't hit. And that's because I did it one instruction too far down, so it was already after the compare. So it was already into check two. So we'd already finished check one, and that's all of the hyphens. So I'll get back to that point. So now it's comparing, hey, is there a hyphen at the fifth element? Yes, there is this time. Great, so we're gonna move on to the next part of this check. And so, hey, is there a hyphen, again, at the bth, which is 11th index? So it'll basically rewind back to 0. It'll reset up, hey, here's the user input. Great, now move to the 11th part and compare that and see if there's a hyphen there.
How did you figure out where to set your breakpoints again?
So I just ran disassemble main, and then I saw there it was calling verify key. So I just put a breakpoint at that. And then when you do SI, that's a single instruction step, it basically sets a breakpoint one instruction down. And so then you just keep going. So then I saw previously where we were failing at this compare against the hyphen. So I just put a breakpoint there, because I already knew what was going on up until that point, so I can just skip over it again. So the rest of check one is checking all of the places where a hyphen should be. So we know at the fifth element, and at the 11th element, and at other elements, there needs to be hyphens. So I made notes of this. This is a different one. This is actually from the TAMU CTF. This is the crack Z code. So all of my notes are here. So I knew at check one is checking for the format of hyphens and checking to make sure it's greater than 28. And then check two was if something that in my mind I called things, which I don't remember. Oh, no. So it was the very first character. So the first character, it was subtracting by 0x30. Remember, this is just 0x41. And then it was checking to see if the result was less than 9. So one valid character that would be there is if we check back on the ASCII table. So we find 0x39. So the maximum valid character that can be there is a 9. So we know the first one has to start with 0 through 9. So now we have 0 through 9, and then we have 4 more characters, like B, C, D, E, and then we have to have our hyphen. And then there's a check if this one is also less than 0x39. So we know this one is also likely to be 9 because it's the same check. So it's probably looking for the same character there. And you just keep going. And it's very time intensive. But that is reverse engineering. That's all that I have now. Yeah, I'll just let this play out and you can watch me try to figure things out. I never figured it out yet, actually. But yeah. I got to like check 5 and I gave up. Because I put like 4 or 5 hours into it. Any questions? Do you understand what assembly is doing? You just, if you don't know what a function or what an instruction is, Like, I don't know what MoveZX is. Just look it up in the Intel instruction manual, and you'll know exactly what it does. It looks like it's just loading things from the bottom part of EAX and zero filling the rest of it. So it is actually taking all of our A's, and then it's taking the lowest part and zero filling. So it would actually be, remember it's 32-bit. So this is 4, that's 8, that's 12, that's 16, that's 20, 24, 28, and then we would have our 4-1. So it's just zero filling, probably. I don't actually know, but that's what it looks like it's doing. And how do I know that? Because this isn't showing any zeros in the front, but it was showing a bunch of A's earlier, and there's a Z in there. It's a lot of guess and check stuff. How do you learn it? You just do it. You have to sit down, you have to do it for like 12 hours straight. After that 12 hours, you'll be like, wow, that sucked. And then you'll be like, I kind of want to do that again though. So you do it again, and then you do it again. And then you're actually kind of good at it now. And then things come easier. And that 12 hours takes you 30 minutes. And you're like, wow, I was dumb before. That was bad. Yeah. And so, as a little spoiler for April 6th, if you reverse the previously given binary, you'll see that it's taking the first 2 bytes and it's treating it as the size that it'll take from the user. So I just set it to be like 500 bytes. Just give it a whole bunch of input. And then I have some shell code. So that's stuff that it'll execute. It'll treat this part as instructions. So if we were to disassemble this string itself, it would be push EBP. It would do all of the same normal setting up a stack for a function stuff, and then it'll just start executing stuff after that. So if we cat the exploit and pipe it into the program, the shellcode it'll copy all of the bytes, it'll overwrite all of the things, it'll overwrite the return address, so it returns to code that we know and control, and then it sets up shellcode for it, and it drops us to a shell, or dies, one of those. And we'll talk about that April 6th. So there will be reverse engineering on April 6th. There will be a lot of frustration on April 6th. But hopefully at the end, you will get to a point where it doesn't actually die on you. And you can actually say that you reversed something and that you wrote a working exploit for something. So please come. It'll be fun. Yeah, I'm going to stop talking now.